Alright. So, simplest slash most straightforward way to prevent overfitting.
I'll just put the date.
Alright, we all good? Alright, just throw them in the middle when you're done.
Oh shoot, it says right in 1 second.
You good? Well, I even forgot that I wrote that. Okay, good.
Oh.
I was like, why is it taking them so long to do it? Just put down A, B, C, or D.
Oh, is that what we're supposed to?
Yeah. No,
thought
no,
it
you're
was
good.
just-
It should do the sentence. I just forgot what I wrote. I try to do these around 3 weeks in advance-ish, just to keep up for when midterms come around and I have to stop making them. So.
It's all one sentence, just a very long sentence.
That better be a freaking like Nobel Prize winner, man.
Oh, by the way, for
Also-
our new students, I usually bring candy. I didn't today because I forgot, but
No,
Normally
Oh,
there's
okay.
candy
Actually, I'm
involved.
just gonna go to the OS lecture.
Okay. You see, Professor Gustavo didn't show up because he somehow knew you weren't.
exactly.
Yeah.
He's
Oh, yeah, no, I was gonna ask if Gustavo really shows up.
Yeah, it's whenever he's like available.
Um,
So, let's try to answer this. Anyone anyone confident? Anyone feeling lucky? Well, I can tell you what the answer is, and then one of you have to give me the sentence. The answer is adding to the tracking set. Ding, ding, ding.
Yeah.
Why might that not always be possible?
Was that you?
Who wants
Okay,
to-
I actually wrote an incorrect sentence. I thought it was why is this correct instead of why is this not possible.
Oh,
Just never mind.
My idea was, so funny enough, I actually put down the wrong letter, but I think I have a correct explanation. Essentially, if you have a really small training set, or if you have a training set which only covers like a few choice scenarios as opposed to like all different kinds of edge cases your algorithm might encounter, then whenever it sees a real world example, it might just try to tack it too much to what it's seen previously. Or like if you have a really small data set of like, maybe 3 or 5 rows, it maybe just try to just Global exams too much.
Yeah, you
I
can-
don't know,
it's
Larry.
not
Good try,
possible.
good try.
Why is-
If your data isn't a good representation of the space model that you're looking at, you need more data. If it's just like a smaller subset of it, it's gonna overfit to that small subset.
Yes, but what, oh,
Oh,
Slap.
my laptop's down. Is it gonna go up? Yeah, but why is it not always possible to add more data to the training set?
Cause you may not have the data, or,
That's, well, yeah,
Like a dynamic data set, you can't like add to that.
If the data is like physical in nature, or like, you know,
exactly. Or if it.
car crashes, you know, like
Yeah.
that's generate more data.
That's a great example, yeah.
yeah.
Yeah, you definitely, sometimes it's very expensive in money or in your
Time.
case, human life, to generate more data, so. Thanks, Steph, how are you doing? Sometimes it's hard to generate more data, so we have to just do what we can with the data we have, and that's where a lot of these other methods come in, except for this one, which has nothing to do with anything really, but that's where these other ones come in.
By the way, yeah, did you introduce yourself, Sean?
Hi, I'm Sean. Nice to meet you. I know like half of you from other things. but yeah.
Okay. Yeah, the other thing is that Sean asked me if we could get accounts in the,
Scholar cluster. I can talk about
okay,
that.
okay.
Yeah. So there's a computing cluster that everybody on campus can use for certain classes. I used it when I took 373 2 semesters ago, or whenever that was. Currently it's down, so I was going to try to demonstrate it, but I guess not. But when it is up, you can set jobs. So like if for when you do the later project, if you want to do like a lot of training on a neural network and you don't want to like, I don't know, clog up data or your own computer and make it run like a jet turbine engine, you can use that. I would also say one more thing that we can use while Scholar is down is cuda.cs.purdue.edu. It has 6 Titan X's on it, and you can use those. So those are like really good GPUs for training, and I think that we all should have access to that as students. So just don't abuse it, but like we have 6 Titans that are just waiting to be used.
So it's cuda.ca.purdue.edu. Okay,
Yeah.
who is currently using it?
I don't know. I didn't check, but I think it's just general use, like the 6 GPUs. I could ask Victor
Okay.
about it, but I just know we also have access
Okay.
to that.
Okay, the Scholar, I actually use my password.
Yeah.
Is that the password, the
Yeah.
career password? Okay.
Same stuff.
So it's a safe thing that you can type your password
Yeah.
there and.
We used it in another CS
Okay,
course. so
okay,
yeah,
okay. But now it is down, right?
Yeah, for whatever reason, I couldn't access even the web page. It's all.
They have many notes in there and somehow they is down there.
I don't know. Yeah. So I was
Okay, well
gonna-
that is another alternative if you don't want to run your. But anyway, what they are going to be doing in this class is not to
Well,
heavy, right?
style transfer might be hard.
Maybe the projects,
Okay,
right? Mhm.
so real quick, I do want to continue because we might run over today
Okay,
already.
okay.
But I was able to get style transfer to work running on this laptop while in cabin in Utah. So you can do it. It might just take a couple hours to train the dang thing. But yeah, that's a really good alternative to have if that works out. That sounds really helpful. So let's start here. Does anyone know these 2 fine people? That's good. That's really good that you don't know them because they're not real. These are faces generated by a neural network. This is the state-of-the-art in face generation, and probably the best of the results that they got from their paper. I can't tell that these aren't people. I could not tell you. And the interesting thing is this is actually using similar technology to what we will be using in the style transfer lab, but it's notable that at this point it's able to generate human faces that a human can't tell the difference between. So that's just something to start off with. Yeah. So today our main topic is going to be optimization and mainly working with the hyperparameters. We're going to talk a little bit about different types of neural networks because so far we've basically talked about one type, maybe 2 types if you count a single neuron as a neural network. But we're going to talk about a lot of different types. But first, I wanted to do a little bit of an addition to our lecture 2 because we talked about neurons as and neural networks as a data structure, and we talked about it as a function. But there's another way to look at it that I think is pretty important, and that's neural networks as a shape. So let's start with that. So I plotted some data here in two classes. It's pretty easy to kind of see a divide between them, right? So if we want to, if our task here is just to split these two sets of data up, where would we want to put that line? Right about there-ish. You could probably do a straight up one as well, but it looks somewhat like it would work like that. So we could do that line, -x + 4. That works just fine. And if we wanted to look at this as a neural network, we could just see it as a single neuron with a -1 weight and a +4 bias. Easy enough. We can just use that neuron as now a line for us. But we can't model everything that way. So in this case, this data, there's clearly a pattern to it. We have the blue class on the outside and the red class on the inside, but it isn't linearly separable. We can't draw one line through that's going to separate those perfectly. We can try this. We can have our x squared going on there, but neural networks can't really model that because we can't multiply inputs together. We can multiply inputs by weights, and you could sort of model this if you had enough neurons that you can just keep multiplying them together, but it's not going to work with more and more inputs, and it's not going to work very well overall. So that's not really an option. But we can do this. Here I've got two lines, which can be represented, of course, by two neurons, and then we would have another layer that would act as the controller, basically, between, all right, if it's right of this one, but over here, or left of this one, but over here, you know. So we can do that with a neural network. We can make these structures out of these straight lines and these more and more complex shapes. Here's a little representation of how we can make more complex shapes like that. If you have 3 hidden neurons in this hidden layer, I think this is only one hidden layer for this one, but if you have 3, we can make a kind of blobby shape there that can get a good portion of the data, but it's not going to be perfect. 6, and you can have some little outcroppings, and 20, you can match it almost perfectly, though this could almost be overfitting. You want to worry about that, especially if some of these end up being outliers. Also important to remember, I'm showing this as a 2D graph, and that works with 2 variables, or an input and an output, however you want to see it. But when we're working with real data, like if we're working with an image that's 10 by 10 pixels, that's 100 pixels. If it's 100 pixels, that means we're working with 100 dimensions. Every attribute of our data is going to end up mapping to some dimension. So these shapes need to be very complex a lot of the time, especially for images, because the dimension space is huge. So this is a really cool website, and I just want to show you guys a little on it first, because it's going to, I think, help in showing how these can model shapes. So we have a few data sets loaded in over here that we can use. In this case, we're going to use this little one here. And let's start with a very simple neural network. We're going to start with just these 2 hidden layers here with 1 neuron each. And we try to train it, and it does not do very much. It can make that line more or less, but it's not getting us all the depth we need here. So let's try with 2 neurons. Now I can use those 2 lines and have them controlled by this other neuron here. And we have our little divide there, which is pretty good, but it's not perfect yet. Now, if we used, I think 3 will handle this one, right? Nope. 3 will almost handle this one. In fact, I bet it would converge eventually, but we're not going to try to make it do that. We're going to just add another neuron, and we might need one in this layer. There we go. So the more neurons we have in these hidden layers, the more complex shapes we can make, but also the more information we have to work with, and therefore the harder it can be to find a good convergence like this. For example, and by the way, these can kind of show the different shapes that each neuron is working with. So we have this one that's kind of made a here line, this one made another one over here. These ones are just dividing it up and down. Yep.
So this is the case of a neural network where the individual nodes are actually human interpretable, or like.
They're not
How
quite
they
human
do that?
interpretable. So basically, these are just representing the weights that each have. And it's pretty easy to interpret a neural network that has data where it's just negative, positive, 2D graph kind of thing. Because you could totally look at a neural net for a car or something that's driving and try to figure out, okay, what does the weight of this and this interacting do? You could go through it by hand, but it would take you years probably, because we're working with thousands and thousands of neurons versus this where we're working with 6.
Okay.
Yeah, but it's a good visualization tool. Of course, then we have ones like this that are very difficult. I'm not going to try to mess with that yet, but adding too many neurons can be a problem. So this could easily be solved with this neural net, I think, right? Yeah. That one doesn't have a problem because it's just a line. However, if I do this, if I try to throw this huge neural network at this tiny problem, it's still able to figure it out actually, but let's try with this one. Oh, all right, this neural network's been better than it normally is. Usually it can be much more of a problem to train it when you are working with making too big of a neural network, but in this case, this website has decided that it likes me today too much. So we're gonna leave it there so we don't run over time, but definitely play with this outside, just if anything, because it's fun. But, oh, and anyone who can get a somewhat nice looking solution to this, you don't get bonus points, but you can feel better about yourself. You know, it's a really hard one for it to learn. It can do it, it's just, and then usually it ends up looking real janky, the shape, but it's a hard data set to learn just from the X1 and the X2. It can be a little easier when you throw in the different inputs you can give it, which is also something you can consider when working with neural nets. You can do like, all right, I'm going to have this input be some extra piece of information from this image or whatever. All right, back to the slide. Hyperparameter is a real subject for today. So, what is a hyperparameter? This is some variable or parameter to our network that is going to be we're going to set it before we do any training. It includes like the learning rate, it can be the number of neurons in a hidden layer, number of hidden layers. It can be the loss functions, activations, anything like that. And that's going to shape what our neural network is structurally. It is not going to include the weights because we use the weights for training. So there are 4 main ways that metaparameters are figured out. I say metaparameters, hyperparameters. I don't know what a metaparameter is. First way is just to manually select it based on prior knowledge. That's used a lot. Like they're usually in the different, for different parameters, there'll be well-known things that are good for different tasks. You can definitely look those up pretty easily, though some of them it's definitely up in the air and you just have to try a lot of things, which is another strategy. Identify a range of possible values and try all of them. You can perform a random search, of course, and just keep trying different ones until you find one that's pretty good. You can use Bayesian optimization, which is not something we're going to be getting into, but it's a little statistical trick that can get us a pretty good hyperparameter value. There are also some less common ways that can be fun, but again, we won't be talking about them in detail. My favorite being the evolutionary algorithms. You can basically use them to evolve the neural network's hyperparameters to a point where it works very well. Those haven't, to my knowledge, done super well in the past, but they've definitely, it's an interesting concept, and I wouldn't be surprised if eventually there was some sort of breakthrough with it. For the scope of this course, though, anyone know how to pronounce this word?
Fingerspitzengefühl.
Very good. This guy takes German. So this word roughly translates to fingertip feel. It's used a lot in business and such. The basic idea is someone who has Fingerspitzengefühl, that I apologize for my bad pronunciation, is able to control things with strong intuition, instinct, and tact. In this course, I hope to have you guys hone your Fingerspitzengefühl for hyperparameter selection. In other words, just kind of try some stuff. Start with something, maybe try to figure out, use your prior knowledge of the problem, of the images, of the network structure you're using, and see what you can do with it. Get into some specifics here now. Learning rate. Learning rate is going to be, of course, our multiplier. We've talked about that before. It just multiplies by our gradient, our adjustment, to create our adjustment. A lower learning rate is going to make the network learn slower. However, it's going to be a lot more fine-grained. It can move to much more niche parts of our learning curve. A higher one is going to, of course, have faster learning, but again, it can overshoot or not be in the perfect direction we want. It would be the perfect direction, but it's going to end up going, it'll overshoot. So a lot of the time, what's going to end up happening is you'll use a decaying learning rate, where it'll start at a higher value, and as the neural network learns more and more and more, it'll eventually switch to a lower value and decay over time. There are other things you can do besides this, but this is the most commonly used option, and or just setting a specific learning rate. Usually it's going to be pretty low though. 0.1, 0.01 are pretty common, especially for starting. You usually don't want to go more than that, because it can be a bit much. Unless you're really going a simple data set, in which case you can just make it 1 and not have a learning rate, but you usually want to make it pretty small. Loss functions. We've talked about them before, but we haven't gotten into it too much. Let's see what the difference is between all of them. Mean squared error. I think we've worked with this one before. I think this might be the one we were using on the project. Oh yeah, it's on the homework too, I think. Yeah.
Mm-hmm.
This is the average squared difference between the predictions and the actual observations. Basically, it extra penalizes predictions that are very far off. And that's mainly because of this nice squared we have here. You could even, if you wanted to mess with it, you could make it like mean cubed error or something, but that sounds a little crazy. That would be if you want anything that isn't really close to be extra penalized. And it's also continuously differentiable, which is nice because we're going to have to, as you know, do gradient descent on everything in the network. So it's nice that we don't have to do predictive values or anything like that. Mean absolute error, not continuously differentiable, sadly enough, but it is going to not punish outliers as much as mean squared error. It's the only real difference, though, is it's just going to be linear instead of exponential. It's still going to be positive in both directions because the absolute value. Cross entropy. This is used a lot, and I suggest at least trying this in pretty much everything you're going to work with because it's performs very well. It's used especially for probabilistic classification, but it can be, there's a different version for binary classification as well. It decreases as the probability approaches the true value. So it's gonna do the same kind of punishing things that are very off, but specifically it's going to extra punish things that are both confident and wrong. So if something's wrong, but it's the neural network's outputting like a low probability for it, it's not going to punish that as hard as something that's like, yes, I'm sure that this is right, and then it's not. A couple other quick ones. Hinge loss, Huber loss, they've got their own little specific niches. Exponential loss is used sometimes, mostly with AutoBoost. Cosine distance is fun because you can talk about the angles between different data sets, but those are mostly kind of fringe ones. In which to use, it depends on the problem. It doesn't hurt to start with cross entropy because there is a binary version that's pretty good, and it works very well for anything where we're doing probabilistic classification. If you aren't doing probabilistic classification, you can also try MSE. It's pretty good. You can do MAE if you really don't want to punish outliers, outlier heavy data, but otherwise you can mostly work with like those two or those three. Weight initialization. So we have our weights. What are we starting with? Well, naive solution would be just slap zeros on them. The tried and true programmer tactic of just zeroing out your arrays, but that doesn't quite work here. If we have all of the arrays all of the weights starting at 0, the gradient as it goes backward is going to it'll have the same adjustment for every neuron in the layer. So what's going to end up happening is the whole neuron is just going to be one linear model. And that, as we saw from our non-linearly separable data, is not something we want at all. So the other option we have here, the most commonly used by far, is just random initialization. Usually that's from a Gaussian distribution, just grab values from that. There are problems that can cause. We're not going to get too much into them just this lecture, but the basics of them is we have vanishing gradient, in which our gradient values as we go back in the network become smaller and smaller until they don't matter at all, or exploding gradient, which is just the opposite during feed forward. There's another solution that's pretty recent, this he et al. Initialization. It's still random, but the range is based on the size of the layer. I'm not going to get too far into that, but if you want to look into that, I've got the link there. Definitely, if weight initialization is something you want to look into, then absolutely. It's an interesting modification that could definitely lead to neural networks being trained faster. All right, hidden layers, number of hidden layers specifically. We also have neurons per layer, but both of them are pretty important. So I can't give you a tried and true rule for these. This is going, but as we saw earlier, the more neurons you have in a hidden layer and the more hidden layers you have, the more complex shapes you can make. Generally, as you saw from the playground thing, the first layer is just going to have like lines, the second one might have combinations of lines, and it can grow more and more. So basically, the more neurons you have, the more patterns you can store, and the more layers you have, the more complex patterns you can store. And it would move up like that, and you kind of have to just, again, Fingerspitzengefühl, kind of figure it out and work with it and maybe try some different things, but you can usually work with less layers than you'd think. That's my only advice from what I've done, is you don't need as many as you'd expect. Though you might need a lot of neurons in those layers. Yeah, oh, and if the problem is linearly separable, you can just use a one neuron. It can always handle it. Or one layer. So activation functions now. Again, we've discussed these before, but let's look into them a little more closely. We have sigmoid. That is going to constrain our output between 0 and 1. Also, it's nice because, again, it's differentiable, and it usually works pretty well for the task it's used for. It's, again, 0 to 1. If we want to instead have a negative 1 to 1 for whatever reason, we can do that too with tanh. ReLU is used very often these days. It is not continuously differentiable, which means usually at this point you just call it 0, even though it's not 0. You'd say anything past here is just gradient 0, but this is the speed at which the network's going to converge. It also, which is mostly, of course, because you have to compute all these functions when you're running this, usually a lot of times, and finding the maximum between 0 and a variable is not computationally difficult. It is much more to do with your sigmoid, where you have to actually have e to the negative x in there, and this still isn't bad. This still is going to compute pretty fast, but not nearly as fast as this. Though often ReLU isn't going to end up being our actual output. It can be, but usually we're going to have something else at the end. Softmax is the biggest one, but we'll talk about that in a bit. ELU. So maybe we want a continuously differential version of ReLU. So in that case, we just make it a piecewise function. It's x if it's greater than 0, and if it is less than 0, we are going to have it e to the x minus 1 times some multiplier. You can kind of pick the multiplier. I had it as 0.5 here, but that's just going to depend how much this swerves down. I don't think that's quite as commonly used as ReLU is still, but it's another option you have, another tool in the tool belt. Softmax. This is almost always just put on at the end, last layer. And that is because what this can do is take your output and squish it into a probability distribution. It's all going to be less than 1 and add up to 1. That's how we do things like probabilistic classification. So if you've ever seen like neural network on some TV or whatever, or Jeopardy, the Jeopardy one, Watson, it would show like it's it would pick its best answer, but it would usually show like other answers under it and say like, yeah, this one's 5%, this one's 3%. That's what it's using at the end. It just put softmax at the end and it can split it up. So yeah, we have a bunch of others that are used. Variations on a lot of them end up happening. Like there's a dozen different ReLU variations. Cosines occasionally used for if you have a weird wavy sort of situation you want to work with. Step functions are fun, though they are not continuously differentiable, so that can make it difficult. Yeah. For image processing, we definitely want to use softmax at the end, and usually we're going to use ReLU in the middle. That is I think most good image processing networks end up using some combination of just ReLU, and then if they want to have a probability distribution, throw softmax at the end. But yeah, experiment, definitely. You can mess with this and see. Maybe you'll find the breakthrough activation function, but this is the most common. ReLU is the most common one we're going to be using. Okay, optimizations. How do we make our neural networks better? Well, one-hot encoding is certainly a way. I think we've talked about this in the past briefly. Again, we just have our vectors. We have them all zeroed out, and whatever value that category, that value represents is going to be in the index of its category. So if we have 0, it's going to be in the 0th spot, 4 would be in the 4th spot. And you can use this for labels too. Like if you had cats and dogs, say you could have two size array with first index being cat, second one being dog. And again, this is basically just breaking it into, instead of being a numerical value, it's a binary value. It's, is this a cat? Is this a dog? Versus it being, is this a cat or a dog? Yes. And if we combine that with softmax, we end up getting that probability distribution we were talking about. Basically, at the end, we would encode all of our true Y values as one-hot encoding arrays, and when it would generate them, it'll generate the probability distribution over those arrays and say, okay, what's the probability of it being in this class or this class or this class? Coding with images. Yeah, for the classes we're going to use it a little, but for images, usually if we're just working with the image, no extra data, we don't need to one-hot encode everything because it's just going to be pixel values. Dropout. So I think we've talked a little bit about overfitting before. The issue with overfitting is that the neural network learns the training data too well. It is, as we saw earlier, where we had that weird shape where it was just kind of spreading out all over the data set. It might put more into the outliers than it should, or it might just think that the training data is, it's not going to generalize to the problem. It's going to fit the training data to exactly. And because neural networks are such powerful learners, they're going to do this a lot, especially like CNN. So dropout is very necessary with these. Basically, you're going to have random neurons just stop firing during every execution, every training execution. They're all going to fire during testing, of course. And it's going to make the neural network not rely on one or two specific neurons. It's going to make it so it has to have a dynamic solution, which is usually going to be then more general. Yeah, the bottom sentence is probably the best one here. Is reduce the power of the individual neuron, making the rest of the network improve. And this is really easy in Keras because we can just add a layer that is a dropout layer, and it'll handle that for us. You can definitely have multiple of these in a network. You're going to want to have it like after convolutions and stuff. But it's a nice little addition. Mini batches. So we can theoretically train a neural network all at once. We could throw all the input in at once and it'll just go through and do all of its matrix operations and train it. But that usually doesn't work well, but neither does just doing one input value at a time. You usually want to do batches of these. So what you'll do is use some set-sized mini batch and maybe 100, sometimes nice. You'll just give it that many inputs at once, it'll train on that, then you give it another set of those inputs, it'll train on that, and keep doing that over and over again. By the way, a little terminology, I think I've covered it briefly before. If once you've trained all of the data once, you've gone through every mini batch one time, that's called an epoch. And you're going to want to train lots of epochs. So you're going to want to put the data through several times because it's going to need several looks at it. Remember, we're only taking little steps with our gradient descent. Oh, important note there. The batch size and the learning rate interact. In fact, there was a recent paper showing that if you don't want to decay your learning rate, you can instead just increase your batch size as you go on. That should give similar results, and that can be good if you want to start with a bigger learning rate. It could be faster theoretically. Yeah, so should be selected randomly if you can. It wouldn't ruin anything if you just selected blocks of it. I think I gave you a mini batch generator in the project for your custom neural network, and I think that one's just grabbing them sequentially. But yeah, usually I start with 100. That's just my go-to. But sometimes 64s use 128 for the different sizes, and you can experiment definitely with that. But it shouldn't be too much bigger or smaller than that area. All right. Finally, let's talk about different types of neural networks. So far, we've only seen the simple ones where we have layers of simple neurons or just one neuron sometimes, and using that for classification only, really. But these are not even close to the only ones. We have not only neural networks that do different jobs, we have different structures of ones, different neurons you could have in them, different parts you could put in the neurons, all that. So let's look at a bunch of these types, and all this information pretty much is from here. You can look up more on them there, but just wanted to cite real quick because they've got good graphs. So we've seen definitely just one single neuron with its inputs. We've seen a simple one hidden layer and an output, and we've definitely looked a little bit at these bigger ones where we have many layers. But how about recurrent neural nets? These are going to take their own output as an input the next time step, which is giving them a very limited form of memory. Kind of works if we're looking at this in the functional way we were talking about as a recursive function. And again, this is like a meta type of network. There are lots of different versions of RNNs. And they can be very useful because, I think the next slide, yeah. You can have variable size inputs for these. As we've seen before with the neural networks, you have to specify an input size. With these, we can say, all right, xt is going to be the input and a is our actual network. output's gonna be HT, so we can just keep putting in the different inputs, and it can memorize what the last one was supposed to be and keep that as the input, keep the state moving forward. Though it's going to lose information over time. Different ways of handling that, but we'll definitely get more into RNNs quite later in the future. Specific type of RNN, long short-term memory models. They selectively remember and forget pieces of information by having inside special gates that decide what the different neurons do. And those gates also have their own weights and activations that need to be trained. But it makes these able to do really weird stuff, especially they can do fun stuff with text processing. I saw one guy, I think he used an LSTM, he put a bunch of Christmas carols into it and had it generate its own Christmas carols. And these are really good at figuring out the structure of English, but not the meanings of the words. So it would just use, it was like the weirdest, almost Lovecraftian Christmas carols you could ever imagine. They were very foreboding, actually, but definitely look that up if you have a chance. But yeah, LSTMs can be weird, and I don't think we're doing any sort of project with them, but if you want an excuse to use them in your final project, for sure, they can do weird stuff. Hoplite networks, or Hoplite, that is a Greek soldier. Hopfield networks. This is going to be basically a network where every neuron is the input and the output and the hidden layer. They're all connected, and it's input during training, input before training, hidden during training, and output after training. And it can actually be pretty good in image recognition. We aren't going to really get into those because they're kind of niche, but they're definitely a nice little weird variant. We have Boltzmann machines, and also restricted Boltzmann machines, which I don't think I have a slide for, but very similar to our Hopfield networks, except we are going to have actual hidden units to do computation that aren't going to be inputs or outputs. There are some more differences, but again, outside of our scope. But yeah, we have hundreds and hundreds of variants, especially when you consider all of the different activations and the different loss functions, all the different parameters we can set and neurons we can use and different structures we can work with these. And that's part of what makes them so dynamic and powerful. We're going to look at some of them more in the future. Some of them we're going to ignore. But there's one elephant in the room we haven't discussed. I'll leave you guys on that for this week.